Welcome to this presentation on the achievements of the 6G-DISAC project during its first 18 months. My name is Henk Wymeersch and I'm the technical manager of the project. This presentation is structured in two parts. First, I will introduce the project and its broader context. Then I will highlight some of the main achievements from the first 18 months. For more detailed technical results, I encourage you to watch the individual work package presentations. Let us start with the background and key concepts behind the project. ISAC stands for Integrated Sensing and Communication. The main idea is to combine sensing and communication within a single system. Compared to separate systems, this can reduce hardware costs, save resources, and create important cross-functional benefits. In this context, sensing can broadly refer to inferring properties of the propagation environment from received signals. In our project, however, we focus mainly on radar-like sensing, as shown on the figure on the bottom right. For example, from radio signals, we can extract information such as ranges, Dopplers, and angles, which can then be used to detect, localize, and track objects or users. It is also important to note that ISAC can be realized at different levels of integration. At one end, shown on the top right figure on the left side, communication and sensing functions may simply be co-located, for example, by combining a base station with an external sensor, such as a camera. On the other end, shown on the figure at the extreme right, the same waveform and same time frequency resources can be jointly used for communication and sensing. ISAC is expected to play an important role in future 6G systems. First of all, sensing information can directly improve communication performance, for instance by reducing overhead and enabling more efficient resource usage. Beyond that, ISAC opens the door to a wide range of applications, including UAV detection, automotive sensing and smart transportation, industrial automation, logistics, and digital twinning, where real-world environments are continuously monitored and represented in the digital domain. When ISAC is extended to a widely distributed 6G setting with multiple base stations, multiple users, and multiple targets, we move from ISAC to DISAC, distributed integrated sensing and communication. This distributed setting is much richer but also much more complex. It involves transmitter coordination, receiver-side fusion and processing, distributed computation, data representation, compression, and potentially integrating with other sensing modalities. DISAC has therefore emerged as an important topic in recent years and is now gaining strong momentum in both academia and industry. DISAC offers several important benefits. It enables multiple views of the same target, improves sensing performance, strengthens sensing-aided communication, supports new sensing services, and can provide built-in redundancy that can improve robustness and security. At the same time, these benefits do not come for free. DISAC introduces major challenges, including time synchronization, frequency and phase synchronization, waveform design and interference management, limited backhaul capacity, the trade-off between local and centralized processing, and latency constraints. These challenges are exactly what motivates the 6G-DISAC project. 6G-DISAC is a 3-year project running from January 2024 until December 2026. It brings together 10 partners from academia, research, and industry. The project addresses DISAC in a holistic way, spanning physical layer design, distributed signal processing, resource allocation, protocols, architecture, and experimental validation through proof of concepts. The project has ambitious targets, including centimeter-level localization accuracy, multi-band operation, support for cell-free and massive MIMO systems, the use of RIS technologies, and the development of innovative AI and semantic-enabled approaches. The vision of 6G-DISAC is to bring ISAC into reality in large-scale distributed wireless systems with many connected users and passive objects to be tracked. To achieve this, the project focuses on several key innovations. This includes a new architecture for DISAC, semantic and goal-oriented methods for data representation and interpretation, high-resolution signal processing and waveform optimization, protocols and orchestration mechanisms, and 5 proof of concepts that demonstrate DISAC in realistic settings. With this background in place, let me now briefly go through some of the project's main achievements during the first 18 months. In Work Package 2, we have developed a preliminary DISAC architecture. This architecture builds on existing 6G architectural thinking, including from Hexa X2, but extends it with distributed sensing specific elements. In particular, it introduces sensing processing functions, including local processing functions, sensing management functions, and the interfaces needed to support distributed operation across the network. This is an important step towards a practical and scalable realization of DISAC. Work Package 3 focuses on the physical layer. The work spans transmitter optimization, receiver-side processing, and sensing-aided communication. Both model-based and machine learning-based approaches are considered, and the work includes also modern MIMO technologies such as distributed MIMO and reconfigurable intelligent surfaces. Another aspect that is important is that Work Package 3 does not operate in isolation. Its methods feed into Work Package 4 for protocol design and into Work Package 5 for implementation demonstration, while also providing feedback to Work Package 2 in terms of metrics, KPIs, and architectural requirements. Work Package 4 addresses resource allocation from a broader system perspective. This includes protocols, orchestration, and spectrum management. The work builds on methods developed in Work Package 3 and studies how these can be coordinated efficiently in dynamic and heterogeneous scenarios. In other words, Work Package 4 helps translate physical layer advances into network level operation, while also feeding architectural insights back into Work Package 2. Work Package 5 is dedicated to demonstrations and proof of concept development. At this stage, 5 demonstration activities are ongoing. This includes DISAC channel characterization, 5G waveform testing platform, a semantic DISAC platform, a RIS-based platform, and a multimodal sensing platform. Combined, these demonstrators are essential because they connect theory to practice and help validate the project's concept under realistic conditions. The project has also been very active in communication and dissemination. During the first 18 months, the consortium has contributed through publications, standardization activities, communication actions, event organization, and broader outreach. The project has already produced a substantial body of visible output, reflecting both scientific progress and active engagement with the wider community. I hope this presentation has given you a useful overview of the 6G-DISAC project and some of its early achievements. To learn more about the technical details, I invite you to watch the individual work package presentations. Thank you for listening, and goodbye.